Hello students, welcome to the class. So today we will deal with the section 6.4, 6.5 and 6.6 of the chapter equilibrium. So this would be our theory part 4 of the chapter number 6 from NCERT. This is the disclaimer. Now in this section we would be focusing on establishing a relationship between the Kp and Kc. We have already derived the equation of the Kc from the law of mass action. We have seen that part. Now we will apply the law of mass of action to our Kp thing, and then we will develop a relation between Kc and Kp. After that, we will do the most important part. You can imagine this part as the application part, where you would see that what is the use of this equilibrium constant and how do we predict the direction and extent. Extent means how far the reaction has gone. Suppose you are going from here to Mumbai and the distance is 500 kilometer. If you are talking about the extent, then you are telling that okay, I have traveled up to 200 kilometer or I have traveled up to 300 kilometer out of the 500 kilometer, which is the total distance. So basically it is deciding that up to what point your reaction has reached. And second, which is direction. So when you decide that the extent of the reaction is this, at the same time you get the direction also, that whether your reaction will go now further from this point or it will proceed in the backward direction. We will see that thing. First of all, if I talk about the specific topics of the NCERT that we are going to cover, then it would be your 6.4, which is homogeneous equilibria, under which we will see equilibrium constant in the gaseous system. Then we will see the heterogeneous equilibria, in which we will see the application of equilibrium constant and how do we use this equilibrium constant to predict the extent of a reaction as well as the direction of the reaction. After covering these two parts, which is extent and direction, we can easily calculate the equilibrium concentrations. So there is a particular table for it, which includes certain parts. We have to go step by step to calculate that concentration. Now if you have done this all, we will move on to some questions, which is our NCERT question 6.5 and 6.7. So let us begin with the homogeneous equilibria. Now this homogeneous equilibria is self-explanatory in a way. Why? Because you have already listened to this term homogeneous, which means that the whole mixture is having the same phase, and the equilibrium where the mixture is in the homogeneous phase, we call that equilibrium as homogeneous equilibrium. Suppose your phase that is for the mixture is gaseous, then all your reactants and products will be present in the gaseous state only. So all the species will be present in the same phase. Suppose if one is gaseous, then all of them will be, including the reactants and products, both of them will be present in the gaseous state, and this same is true for the homogeneous aqueous equilibrium. Now what is the meaning of homogeneous equilibrium? We know it, but what is the use of it? Why will we study it separately? Is there any reason for it? Yes, the reason is that homogeneous systems are not that much complicated. So if you know that the system is homogeneous, then we can easily calculate the concentration of all the species. I would say equilibrium concentration of all the species, and the reason is that they mix together very efficiently. As a result of it, we will be able to calculate the equilibrium constant and predict the reaction and the equilibria. What would be the example of it? Suppose we are considering the synthesis of ammonia. Now in this synthesis, you can see both the nitrogen and hydrogen that is present on the reactant side, as well as the product, which is ammonia, present on the product side, are present in the gaseous state. Means they are having the same phase, and hence the mixture will be termed as homogeneous system, and the equilibrium related to it will be as homogeneous equilibrium. We can take one more example of aqueous phase. Here we are taking the reaction of iron 3 plus with our SCN minus to give us the complex, which is FeSCN 2 plus. Here also we can see that all these three species, including the reactants and products, are present in the aqueous phase. So we can say that the equilibrium attended by this equation will be a homogeneous one. Now, I have said you that it helps us to calculate the concentration easier, in an easier manner. How do we know it? So let's see an example of it, that how it is easy to calculate in the equilibrium, which is in the homogeneous phase. For that, first we will introduce you to the equilibrium constant, which is in terms of partial pressure. Suppose your reaction is only involving gases throughout its mixture, means all the reactants and products are present in the gaseous phase. Now, if it is the case, then what we will do, rather than taking the concentration, we will take the partial pressure. Okay, because the concentration of a gas is not constant at every point. You can think it of in a simple way. Suppose you are taking oxygen molecules in a given container. At some point of time, it is possible that the concentration at one point of that container will be different from the concentration at the different point of the container. And the reason is very simple, which is the movement of the particle in the gaseous phase, which varies at concentration. So rather than taking concentration, we take the partial pressure. Suppose we are considering the reaction here, A plus B giving us C plus D with their stoichiometric coefficient as small a, small b, small c and small d respectively. Here you can say that this reaction mixture will be a homogeneous one. Why? Because all of the system are present in the gaseous phase. Then similar way in which we write the Kc, we can write the Kp as well. How do we write it? But here what we will take? We will take the partial pressure. Remember, here we have the PC, PD, PA and PB as the partial pressure of A, B and C, D respectively, and all of this partial pressure are raised to the power which is equals to their stoichiometric coefficient. Now similar to the Kc thing, here also we take the pressure of the product on the numerator and the pressure of the reactant in the denominator. You got it? I hope this part is clear to you. And why we are taking pressure? Again, I am repeating it, because the concentration varies. For a reaction mixture, if you take, which is present in the gaseous phase, the concentration varies due to the constant movement of the gaseous molecule. So rather than considering the concentration, we take the pressure. Now we will try to develop a relationship between Kp and Kc if we know both of them. Suppose this was the reaction that we have taken, A plus B giving us C plus D, and we have derived the Kp value for the same. Now if we use the ideal gas equation, which is Pv is equals to nRT, and we write it at constant pressure and constant temperature, then what we can say, that P is equals to CRT. Got it? Why we have written C? Because if you just cross multiply this volume on the right hand side, then we will get a term N by V. And we know that the number of solid particle per liter of the solution is called as the what? Concentration. So this can be considered as the molar concentration of the gas. Further, we know that the Kp expression is Pc raised to the power small c multiplied by Pd raised to the power small d divided by Pa raised to the power small a multiplied by Pb raised to the power small b. So this is the Kp relation. Now if you put the pressure term as CRT, then we can write the concentration of C multiplied by RT raised to the power C for the PC. Okay. Similarly for the D, we can write the concentration, and for A and B, we can continue with the same. Then after doing this, what else we can write? What we can do is put a RT aside. See, if you are taking this RT and RT common, then they all will have a power of C, D, A and B. Now since the base are same, you can just take the individual contribution from each and subtract the numerator coefficient from the denominator one, or the numerator power with the denominator power. Right? Again, why I am doing it? Because we have a same base. So basically you can write this CRT raised to the power C as C raised to the power C and RT raised to the power C separately, and then you can take this RT thing common. If we substitute the value of Kc in this equation, what we will get? See, we have concluded from our previous discussion that Kc is equals to C, concentration of C raised to the power C, concentration of D raised to the power D, divided by the concentration of A raised to the power A and concentration of B raised to the power B. So let's substitute this whole in the previous equation, and you will get your final equation at Kp equal to Kc. Then we have the subtraction of the stoichiometric coefficient from the product minus the reactant. Here, next what we can do for the reaction, if we have included the Kp-Kc relation, then we can just extend it further, and instead of writing C plus D minus A plus B, we can write it as delta Ng, which is change in number of gaseous products minus change in number of moles of gaseous reactants, because this C plus D is the total number of gaseous products and A plus B is the total number of moles of gaseous reactant. Now, substituting this value in the delta Ng, we will get it as Kp Kc RT raised to the power delta Ng, and this is your famous relation between Kp and Kc. Here, what is your R? R is your gas constant. Now you can have its value in terms of 0.0831 liter bar per mole per Kelvin, or 0.0821 liter ATM per mole per Kelvin, or you can write it as 8.314 joule per mole per Kelvin as well if you are writing for its SI units. What about the temperature? So temperature will have the same scale in both the CGS and the SI unit, which is Kelvin. So this is your overall calculation. Now this equation number 6.15 is from the NCERT, and it is very, very important. Here I have just put up a table to represent the different cases of Kp and Kc, and I have taken the corresponding example as well. Suppose you find out that this Kp and Kc are equal, then what can be the case? You can only keep both of them equal if the change in number of gaseous molecule is 0. Suppose for this reaction, if you consider, then on the reactant side we have two molecules of gases, which is one of H2 and one of I2. On the product side, we have again two molecules of products, which is HI. So we can say that the change in gaseous number of moles is 0, and therefore Kp will be equals to Kc. Second case, what we have taken, in the second case, if you see, then the delta Ng is greater than 0. Why? Because we have more number of gaseous molecules on the product side. Therefore, the delta Ng will be here 2 minus 1, which is 1. Or you can say Kp is equals to Kc RT delta Ng. So, your Kc will become equals to Kp if and only if you are multiplying an RT term along with it. So, you have to multiply it with a greater term. Therefore, you can easily say that your delta Ng is greater than 0 and your Kp is greater than Kc. Now, I am leaving this third situation on to you. Just try this out. See that what is the change in number of gaseous molecules, and try to see that what is the relation between Kp and Kc. Is your Kc bigger or is your Kp bigger, depending upon the delta Ng value. Now, here I have a question for you. For the equilibrium 2NOCl gaseous going to 2NO plus Cl2, the value of the equilibrium constant Kc is given as 3.75 into 10 to the power minus 6, and this value is at 1069 Kelvin. Now you have to calculate the Kp for the reaction at the same temperature. Okay, you have 30 minutes to solve it. Your time starts now. You have 5 more seconds. So your time is up. Let's see how we can solve it. Now we have already done with this equation of Kp is equals to Kc RT delta Ng, and if you apply that formula, you can solve this numerical very easily. We know that our Kc value is given 3.75 into 10 to the power minus 6, and we have the value of temperature as 1069 Kelvin. Now, from our previous knowledge, we already know that the equilibrium constant requires the R value, and it is 0.0831 L atm per Kelvin per mole. So this is in terms of what? In terms of liter atm per Kelvin per mole, and not in the SI units. Then next part, what we will do, we'll calculate the delta Ng. So on the reactant side and the product side, just calculate the number of molecules. So what is the number of gaseous moles on the product side? So for Cl2, if you see, then it is 1, and for NO2 it is 2. Therefore the change would be how much? And for the NOCl it is 2, right? So we have this NOCl also on the product side. So on the reactant side, that the delta Ng will be 2 plus 1 minus 2, which will be plus 1. If you substitute this value into our final equation, so what is our final equation? It is Kp equal to Kc RT delta Ng. Now in this, we need the delta Ng value, and we have already calculated this, and this value is 1. What is the value of temperature? It is given in the question 1069. R value we have seen, it is 0.0831, and Kc value is given 3.75 into 10 to the power minus 6. If you put all of this, you will get your Kp value as 0.033. So finally, we have concluded the equilibrium constant in terms of partial pressure as 0.033. So this is your final answer. Moving on to the next type of equilibria, which is heterogeneous equilibria. What is heterogeneous equilibria? So opposite to the homogeneous, in this case, the equilibrium is established in such a situation or in such a mixture where all the species are not present in the same phase. For example, if you are reacting the steam with the red hot carbon, now carbon is present as the solid form and the vapor form is for the gaseous for the water molecule. Okay, so we can say what, that the reactants are not itself in the same state. One is in the solid state and the second one is in the gaseous state. Now in this kind of situation, remember some key rules. First is, the concentration of pure solids and pure liquids are always taken as 1. So this is very, very important to remember, right? So this is the most important point, and this is not applicable to gases. Remember, the gases cannot have a unity, or you can say the similar concentration throughout the chamber because of the moving molecule. This can be only said for the pure solids and liquids, where the movement is not arbitrary. Second thing is, this thing is omitted for the equilibrium constant expression. Now, moving on to the reason why we have said it so, because of its density, which is equal throughout the molecule, equal throughout the element, and for that reason we take the concentration of pure solid or liquid as unity. Now next, what we can say, that the concentration does not change in this situation. You got my point, right? So what we are dealing with? We are dealing with a heterogeneous equilibrium. Okay, and in a heterogeneous equilibrium, we will have different states of different species. And second thing we should remember is that the concentration of pure solids and pure liquids is always taken as unity. Now let us take an example to understand the same. Suppose we are considering the decomposition of the calcium carbonate. This can be represented by the equation: calcium carbonate present in the solid phase is decomposing to form the calcium oxide, which is in the solid phase, and the CO2 which is in the gaseous phase. Now can you identify whether this reaction is homogeneous or not, or it is heterogeneous or not? Just look on to it. It's very simple. Meanwhile, what can be the equilibrium constant expression for this? So you can write Kc is equals to concentration of calcium oxide multiplied by the carbon dioxide gaseous phase divided by calcium carbonates in the solid phase. So this is the term for Kc. Now I have already told you that the solid will be taken as unity. The concentration of solid will be taken as unity. And students, for those who have thought about this equation, this is a heterogeneous one. Now if this is taken as unity, the concentration is taken as unity, we can simply write the equilibrium constant Kc is equals to the concentration of CO2 in the gaseous phase. Now we will use the formula of Kp. Kp is equals to Kc RT delta Ng, and for the reaction, which is calcium carbonate going to calcium oxide and carbon dioxide, we can say that delta Ng can be written as 1 minus 0 because there are no gaseous species on the reactant side. Next, Kp will be equals to CO2 RT raised to the power 1. So this is our general equation, Kp Kc RT delta Ng, and delta Ng is taken as 1. Now next, what we can say, if you want to substitute this concentration term, then we know that P is equals to CRT, and instead of C, we can write pressure of CO2 by RT. So we have done that same thing. Okay. So finally we can write Kp is equals to P COT. Here the RT terms get cancelled out. Is it clear to you? So we have got our relation for the Kp, which is pressure of CO2 simply. Now this is your final equation. Is it clear to all of you how I have deduced this final equation? I hope you are getting the point, right? So first we have calculated the Kc, where we got the concentration of CO2 only, and in the Kp also we got the pressure of CO2 only. Why? Because your solid species, right? Your solid species have no application of pressure. They are not applying pressure on its wall. And same is true for the liquid as well. Now moving on to the application part of the equilibrium constant. So we know that equilibrium constant is calculated using the formula of Kc is equals to product concentration by reactant concentration. But what is the use of it? Why are we calculating it? So that is the most important part. Now remember one thing, that there are some features which you should remember about the equilibrium constant. So it is only applicable to those equilibrium mixtures which has attended the equilibrium condition. That is, no net change in the physical properties. Next is, this equilibrium constant has no dependence on the concentration part. You can take any concentration value, but the Kc value will remain same. Third thing, it is dependent upon temperature and on the balanced chemical equation. If you are changing the balanced chemical equation by multiplying by any factor, then you will always see a change in the equilibrium constant as well, and same is true for the temperature. Moving on to the application part. So first of all, it helps us in predicting the extent of reaction, and we will see to it how it is helping us. Second thing, it helps in predicting the direction of reaction. If you know the extent, you can predict the direction. And third thing, it helps us in calculating the equilibrium concentration, and it's very easy. You will see a table to do the same. So first, what we will start with? We will start with the extent of a reaction. So we are going to see that how do we know the extent of a reaction using the equilibrium constant, and for that you have to look upon this whole illustration. Suppose your Kc value is equals to 1. So there are three situations which is given. If your Kc value is greater than 10 to the power 3, that means your reaction is almost completed. So this is the first situation. Okay. Suppose you have calculated the Kc value and your Kc value is greater than 10 to the power 3. That means your reaction is almost completed, or you can say the product is formed in the dominant amount. In the second condition, what we can take, where your Kc will be less than 10 to the power minus 3. In this case, we say that, okay, in this case, the reaction has hardly proceeded and most of the reactants are present as the initial state. The third case is, the Kc value is between 10 to the power minus 3 to 10 to the power plus 3. In this case, what we say, that nothing is dominating. Okay, means the reactants and products are both present in an appreciable concentration or in a comparable concentration. You can depict the same using this arrow. See, if it is less than 10 to the power minus 3 means your reaction has barely proceeded, or there is neglect amount of this product. If it is greater than 10 to the power 3 means greater number of product is formed. If it is between 10 to the power minus 3 and 10 to the power 3, that means the reaction is intermediate. Neither the reactant is present in the greater amount nor the product. So what you can say from here, that if we know the value of Kc, we can easily depict the extent of a given reaction, that how much product it will form. Now we will look at some examples to understand the same. Suppose we are taking three reactions here. For the first reaction, if you see, then we have this H2 plus Cl2 giving us the 2 moles of HCl. In this case, if you calculate the Kc for the reaction, then you will get it as 4.0 into 10 to the power 31. Remember that this value is specified for a given temperature, and suppose at any temperature we are getting this value. It is any specified temperature, I would say. Now in this case you can easily see that this Kc value is greater than 10 to the power 3. So the reaction will go on to its completion almost. Right? So this is the first situation according to this arrow symbol. If you see we have a 10 to the power 3, and after that we have extremely large products. Then if you look at the second equation, which is formation of NO, in this case the value of Kc is found out to be 4.8 into 10 to the power minus 31, which is extremely small as compared to the 10 to the power minus 3 value. So what we can say, in this situation there is hardly any formation of product. In the third situation, we have taken the formation of hydrogen iodide, where the Kc value is found out to be 57.0. If you see this thing, then what you can predict? That our reaction is not favoring the reactants as well as the product. This means that both of the reactant and products are present in a appreciable or comparable amount. Is it clear? So remember this thing, that if you know the value of Kc, you can predict the extent of a reaction, or you can predict that whether the reaction is reactant predominate or product dominated, or dominated by both of them equally. Now if you now know the extent of a reaction, the second part is predicting the direction of a reaction, which is in equilibrium. Now how do we do this? For that we need to calculate the reaction quotient. So here is your most important term of this lecture, which is reaction quotient. How do we calculate reaction quotient? It's very simple. Suppose if you are defining the QC, it is defined in the same way like your Kc. The only difference is that you are not calculating this in your equilibrium mixture, but at any certain point. Right? So this is your first condition, that your QC will be calculated in the same way as Kc, and it is not necessary that your reaction must be at equilibrium to calculate the QC. Then if this is true, then for a general reaction, suppose we are writing the reaction quotient. So this is your reaction A plus B going to C plus D. Then in that case we can write QC as concentration of C at equilibrium or not at equilibrium. So both conditions are possible, raised to the power small c, then the concentration of D divided by the concentration of A raised to the power small a, and the concentration of B raised to the power small b. So you can see it that we are having a quite good similarity in the calculational part of the Kc and QC. The only difference is that this concentration that we are seeing is not at equilibrium but at any arbitrary instant of the reaction. But the question is same. How do we calculate, or how do we know the direction of reaction if we know the QC? So see, it's very simple. So there are three cases here. Three cases can be possible. The first can be your QC can be less than Kc. Second one would be QC will be greater than Kc. And the third one would be QC will be equals to Kc. Now what is the effect of this comparison? If your QC is less than Kc, that means your reaction will now proceed onto that direction where your product needs to be formed. Got it? Why I am saying it? Suppose your Kc is less than QC. That means your Kc value is less, or how you can increase the value of QC so that it become equals to Kc, or how you can make the reaction mixture go to equilibrium? If you increase the concentration of products, as simple as that. So how do we do it? By moving in the forward direction. In the second case, if you see, then QC is greater than Kc. See here, in the diagram, if you notice, then there is the third bar graph which represents this condition where QC is greater than Kc. Then in this condition, your reaction will move in the backward direction because you are having a greater amount of product than the expected one or than the equilibrium mixture. So your reaction will go in the backward direction or the reverse direction. The third situation is that both your QC and Kc value are having the same numerical value. That means your reactants and products are formed in the appropriate amount. Got it? Clear? Is it clear to all of you? So at this stage, what we will say, that the reaction is at equilibrium and there will be no net reaction. Now let us move on to a question. Suppose the value of Kc for the reaction 2A giving us B plus C is 2 into 10 to the power minus 3. Then at a given time, the composition of the reaction mixture will be A is equals to B is equals to C is equals to 3 into 10 to the power minus m. Then you have to decide that in which direction the reaction will proceed. You are given the value of Kc, you are given the concentration of A, B and C at a instant, and you have to decide that whether at that instant what will happen. Will the reaction go in the backward, forward, or will it stay in the same situation? You have some time to solve it. Your time starts now. It's very simple. Just try to calculate the QC and compare it with the given value of Kc. You will get your answer. We have seen 3 situations and we know how do we compare and find out it. So your time is up. Let's see. In this question, we are given with the value of Kc 2 into 10 to the power minus 3 and the concentration of A, B and C at a certain instant, which is 3 into 10 to the power minus 4 molar. Then we will calculate the reaction quotient first of all. For Qc is equals to concentration of B multiplied by the concentration of C divided by the concentration raised to the power 2 for A. Why are we raising it to 2? Because 2 is written as the stoichiometric coefficient. If you substitute all of these values in your QC, then you will get your final QC as 1. Now let us compare it with the Kc value. Kc value is 2 into 10 to the power minus 3, which is less than the Qc. So what you will say, since your Qc value is greater, therefore the reaction will proceed in the reverse direction. Is it clear to you? It's very simple. This is the first situation. Sorry, this is the second situation that we have seen in the previous discussion. Got it? Now let us calculate the concentration at equilibrium. So this is our third thing and the most important part, I would say. For that, we have a simple method. That method is known as ICE table method, and how it is used. For that, you should know what is I. So I is the initial concentration or pressure. It can be both of them. Then C is the change in concentration of the reactants. And your E, now this change is represented as X. And your E is what? E is your equilibrium concentration, which is sum of I and X. Now let us try to understand this with the help of an example. How do we imply this given ICE table? Suppose we are taking a hypothetical reaction in which the A plus B is going to C plus D, where small a, small b, small c and small d are the stoichiometric coefficient. And each of them is having an initial concentration of I. First of all, we will write the balanced equation. Now suppose this reaction is already balanced, which is your hypothetical reaction, and under the equation, let us list the initial concentrations. So this is your table. In the initial state, A, B is having a concentration of I and C and D are not formed at all, so they will be taken as 0. Then what is the change? Suppose we include this change as X. Therefore, what we can write using the stoichiometric coefficient for the concentration of A, B and C, if the change is X. So if this change is X, then A amount of X will be deducted from your I and B amount will be deducted from the product number B. Then if the coefficient is C, then Cx will be formed for the C and Dx will be formed from the for the D. So what we are taking here is the stoichiometric coefficient. See, these are all stoichiometric coefficient if X is the change. Further, what we can do, we can write the final concentration of equilibrium if Ax, Bx, Cx, Dx are all the change. So final concentration at equilibrium can be written as, for A it will be I minus Ax, for B it will be I minus Bx, for C and D it will be Cx and Dx. Finally, if you substitute this value in the equilibrium concentration, for the equilibrium concentration in the Kc, what we will get? We will get our equilibrium concentration easily using the value of X. I hope this point is clear to you. Thank you for attending the lecture. I hope you enjoyed the session.